Okay, welcome to example 7. We have two blocks that are held still right here, and there's a spring between them that is compressed. And it's compressed 0.09 meters from its original length, where it would be uncompressed. This smaller block is 1 kilogram, and block B is 3 kilograms. And we release them. And when we release them, the spring doesn't attach itself to either block, it just falls straight to the ground. And we know that after it's been released, block B acquires a speed of 1.2 meters per second. So I always like to draw pictures with my problem, so I'm going to draw another picture of this after they are released. Okay, so I've drawn another picture after the spring has been released, so that the spring is essentially down here on the ground, and block A is moving probably to the left. It should be, because if this block's moving to the right and the momentum of the system before they were released was 0, well, if that's a positive momentum, hopefully you'll realize that the other one has to be a negative momentum to cancel it out. So how are we going to find the speed of A after it's been released? And to do that, we need to use conservation of momentum. So we have momentum initially is equal to momentum finally. We're assuming, by the way, that there are no external forces, and that's stated here. That's a frictionless table, so no external forces that are going to slow it down. So the momentum of the system is what initially? Well, you have these two blocks. You could write mass A plus mass B times velocity initial. But what's the velocity initial of the system? Well, they're forced together and they're held together. They're at rest. So the initial velocity is 0, which means the initial momentum is 0. And so afterwards, we do have two individual momentums, and hopefully we'll realize that they have to cancel each other out, because we have to have a final momentum that's also 0 if the initial momentum is 0. So we have the momentum of A, mass A, velocity A final, plus the momentum of B, mass B, velocity B final. And we can substitute our numbers in here. We have mass A was 1 kilogram times velocity A final. And we have mass B, which is 3 kilograms, times the velocity that it leaves at, which is 1.2 meters per second. Okay, so then go ahead and put that in your calculator, and you should get velocity A final will be negative 3.6 meters per second. And hopefully you'll realize that negative is because it's moving to the left. And that's why we have a negative. And that's got to cancel out with that one. Okay, so that's part A. Part B is how much potential energy was stored in this spring initially. And we can't really use 1/2 kx squared, because we don't know the spring constant. Oh, I guess we do. We do know that 0.09. But is that going to solve the potential energy? Well, we don't know what the spring constant is. So how do we figure this out? Hopefully you realize that these two blocks are moving away with energy, kinetic energy. And where did it come from? Well, it came from the stored energy in the spring. So by conservation of energy, the energy initially is spring potential energy. So I'll write US for spring potential energy. And the energy afterwards is kinetic energy. So we have two kinetic energies. We have the kinetic energy of A finally, and we have the kinetic energy of B finally. In fact, let's just put those numbers in here, or those formulas. We have 1/2 mass A times velocity A final squared, plus 1/2 mass B times velocity B final squared. And then we can go ahead and substitute in our numbers. We have 1/2 times mass A, which is 1 kilogram, times velocity A, which is what we just figured out, negative 3.6 meters per second, quantity squared, plus 1/2 times mass B, 3 kilograms, and velocity B was given as 1.2 meters per second, quantity squared. So go ahead and calculate that. And I get the first one to come out to be 6.48 joules plus 2.16 joules. So I wanted to point this out that both of them moved off with equal momenta, different velocities. Why different velocities? Well, because this guy's smaller, so he has to move faster. And they didn't have equal kinetic energies. So they had different kinetic energies, but their total kinetic energy adds up to the spring potential energy. I just wanted to point out they're not the same kinetic energies. They have the same equal and opposite momentum because they're both the same impulse on each other, but different velocities at different masses. Okay, so the total energy will be 8.64 joules. And I could follow up this question and say, okay, now that you know the spring potential energy, I'll just put this as an aside, we could say, oh, what is the spring constant, K? So you could then say, okay, US equals 1/2 kx squared, and figure out what the spring constant is. You have 8.64 joules equals 1/2 times K, and X was given as 0.09 meters, and so you can go ahead and calculate K, although it wasn't asked, but I just thought it would be a nice little aside, and you'll get K is equal to 2,133 newtons per meter. Okay, that's it for example 7.